All right, good morning everybody. Let's get started with our fifth installment, the lecture on game AI. And here is what we are going to do today. As usual, we will begin with a quick recap of what we did last time. And then I'll throw some more terms and definitions in front of you. Once we are done with that, we can then finally study more interesting things. In particular, we will look into the problem of computing optimal strategies for two-player turn-based games and in how far, well, rather famous tree search algorithms can help us with computing these strategies. Then we'll close with a summary. So, what did we do last time? Right, if you remember, we introduced the notion of a game tree, which is a representation of game states and moves, and to which kind of game states these moves do lead. And we saw that we can consider game trees beginning at the initial state of a game, and then a game tree would represent all possible games. Or in the example we considered, we had a game tree that was starting at some state throughout the game of tic-tac-toe, and we took it from there because we could plot it. But game trees are a useful representation of what is going on in a two-player turn-based game. Right? Given that notion of a game tree, we introduced a couple of more interesting or important concepts. In particular, we had a look at the notion of the average branching factor. This is the average number of children of a node in a game tree. So if the number of possible moves a gamer has to its disposal is the same in every game state, this branching factor would be constant. And if in every, say, state you would have two possibilities of what to do next, then the branching factor would be 2. If in every state you would have 5 possible moves, branching factor would be 5. However, with games like tic-tac-toe, for instance, we saw that this branching factor is not a constant, because at the very initial state of the game, the player 1 has 9 possibilities for how to move. So for the root node, the branching is 9. And then the next possible situation, the second player only has 8 possible moves, because one field is already occupied. And then in the next situation, player 1 would have typically 7 possible moves, then player 2 would have 6, and so on and so forth. So we see that this branching factor generally is not a constant. And in that case, we cannot really compute the branching factor, but the average branching factor. And this is what this is about. And we call it B. We also had a look at the notion of the maximum depth of a game tree. That is the maximum depth of any leaf of the game tree. Right? So typically there are some leaves rather high up in the game tree. That is when a game ends quickly, just after a couple of moves. But if a game extends over a longer period of time, the number of moves is rather high, and the game tree, descends further deep. And so there is a maximum depth, and that is called M. Well, I said already that a game may end rather quickly. If one of the players does not really play intelligently, the other player may outsmart him or her and win rather fast. So that is, some of the terminal states of a game might actually reside higher up in the hierarchy of the game tree. We call the minimum depth of any leaf node the shallowest depth. And I use the letter D to refer to that level in the game tree where we find the highest or uppermost leaf. Now that we have sort of reminded ourselves about what we did last time, we can begin to do more interesting things. Right? And in particular, for the next couple of lectures, we shall focus on this typical / traditional scenario of game AI. And that is, we will look at what people did when they first began thinking about using computers to play games. And as it so happens, the kind of games they were considering back then are deterministic, turn-based, two-player, zero-sum games of perfect information. Right? We already saw what it means for a game to be turn-based. We already saw what it means for a game to be a two-player game. We already saw what it means for a game to be a game of perfect information. I did not yet tell you about deterministic games. Well, that is basically to say there's no element of chance here. There's no rolling of dice. Basically, everything the players do is based on informed decisions without any uncertainty whatsoever. These games are deterministic. Then what is a zero-sum game? That is the final missing piece in this bullet point here. What is a zero-sum game? And we need to look into the notion of a zero-sum game in order to understand the things that are to follow. Here it is. A zero-sum game is a game where one player's gain or loss of utility, whatever that is balanced by the other player's loss or gain. What is a utility? Well, basically we can say a zero-sum game is a game where once the game has terminated and we add the loss and the gain of both players, we end up with a value of 0. So we sum gains and losses, they sum to 0, zero-sum game. What is a utility or a payoff? Or more generally, what is a utility or payoff function? That is a rather important concept, rather theoretical concept, because if you are playing a game, you hardly, while playing that game, I don't know, tic-tac-toe, Connect 4, chess, battlefield, battleship, you may not actually think about what you are doing in terms of payoffs or utilities. You may think about what you're doing in terms of, oh, I should move here, or I should do this, or this would advance my state in the game and sort of be bad for my opponent, whatever. So these kind of mental processes will be going on while you are playing a game, but you hardly think of, well, if I make this move, I will gain an advantage of some number. I mean, some of you might do this actually, like experienced chess players. I don't know. I don't play chess myself. But theoretically, we can think about what is going on during, say, one of these deterministic, turn-based, two-player, zero-sum games of perfect information in terms of numerical values, which, in this definition, we do assign to the terminal states of a game. Here is an example. So, if you're playing a game and the game has reached a terminal state, you may have won, you may have lost, or the game may have ended in a draw. Now, a sort of canonical choice of numerical values we could or can assign to these situations is, of course, say a value of +1 if the state represents a situation where you win the game, a value of -1 if it is a situation where you have lost, and a value of 0 where the game ends in a draw. And we saw, for instance, for tic-tac-toe that can happen. The whole board is covered with noughts and crosses, and there is no field left for the players to make their moves anymore. Then it is a draw. Yeah, here is an example. So again, this is the tic-tac-toe game tree we have looked at last time. And again, we do start fairly low down in the tree. The root node of this game tree is a game state in a game of tic-tac-toe, which has been going on for quite some while. here there are already 5 fields out of 9 are covered with symbols placed by the players. Again, we see that obviously, looking at the root node, it is player 2's move, because there are 3 crosses but just 2 nodes. So just from looking at that picture, we know the next player to move has to be the player putting the nodes. Now, 4 empty fields, 4 possibilities for the player to make a move. And then once the player has moved, there are 3 empty fields left. So in the situation after player 2 has moved, in the situation when player 1 is to move again, player 1 basically has just 3 possibilities for making the next move. And then after that there will only be 2 fields left, so player 2 has 2 possibilities. Then there's, if at all, just 1 field left, and whoever is to move has to move to the remaining field. We see that there is a very shallow terminal state, because given the game state in the root node of this tree, it is obvious that player 2 can immediately win by putting a circle onto this field. Right? Then the game has reached the terminal state. This is a win for player 2. And note that I am marking this with an orange +1. But if player 2 wins, then obviously player 1 loses. This is a zero-sum game. So the payoff for player 1 in this particular terminal state of the game is -1. Okay, let's see. Do we have a situation where player 1 can win? Yes. So if for whatever reason player 2 does not seize the opportunity to move over here, but moves to there, then in the next round player 1 could win the game, for instance by placing a cross up here. Again, the game would terminate in that state because one of the players has won. In this case, it would be player 1, or the player placing the crosses, and his or her payoff would be +1. And accordingly, the other player would have lost, so his or her payoff would be -1. And then, of course, there are these interesting situations, these interesting leaf nodes of the game tree, which are sort of rather, characteristic for games like tic-tac-toe, because, as we can see, if both players play smart or intelligently, they may play until the game has reached a state where no further move is possible, because every field on the board is marked, but no player has won. And in this case, the payoff for both of them is 0. And if we add 0 to 0, we have 0. So it's a zero-sum game. The next thing we have to familiarize ourselves with is the idea of a goal state. And that is a terminal state of a game of high utility. Right. What is high utility? Well, typically that means it is a state in the game where you, as the player, win. So a game of high utility is usually a winning state. It then may have a payoff of +1, but depending on the game, for instance, if you play for money, your payoff might be a number different from 1. Right, so I don't know, you play poker, and depending on how the game ends, you might win $1,000 or just 100. It is typically a winning state. You have a high payoff, but the payoff once again does not have to be plus or minus 1. It could be something else. Right? But typically, if you win, say a game of poker, the money you win has to be paid by all the other participants, and if you add wins and losses, it's a zero-sum game again. And so, we can definitely say that a goal state, very abstract idea here, is a leaf node in a game tree of high utility, right? However we measure that. Once we accept the idea of representing games in form of trees, and also accept the idea that we can characterize our desire to win the game in terms of wanting to reach a goal state in such a tree. We can indeed formalize the notion of a strategy. Right? Strategy is one of these terms we use rather frequently in our daily lives. And this is great because we intuitively have an idea as to what it means to have a strategy or to pursue a strategy. We know that strategy has to do with achieving goals and probably making plans as to how to achieve these goals. Now, we can indeed formalize that in our situation. So again, like I said it, strategy can be thought of as a plan of how to reach a goal. In real life, this problem of achieving that goal typically suffers from uncertainty. There are lots of influences that are not necessarily under our control. So, we have to have contingency planning, and I could do this, and if that doesn't work, then I might do this. These kind of reasoning process may go on. And we will see how to do this in the case of two-player turn-based games, where again we are not in control over the opponent, over the adversary in the game. Right? We may make a move, the other player may make a move trying to sort of counter what we just did, working against our goal, pursuing their own goals. They have to sort of plan for that. And that actually leads us to the idea or to the notion of a tactic. This is yet another word we are used to from everyday life, right? But what is a tactic? If we understand a strategy as a plan of how to reach a goal state, we can think of a tactic as a plan, again, of how to reach a sub-goal that would, take us closer to our final goal. And again, you may have a strategy for how to reach a certain goal, and you may have had lots of ideas as to what will happen throughout the history of things to come and what to do when, but you're not entirely certain as to what will happen because opponents may, have their own strategies. So in the context of games, throughout a game, eventually certain uncertainties become certain. And you say, okay, so this is something that is not fully in line with what I have been planning for, but given that I now observe this situation, I probably should do this. This is a tactic. Right? Once certain things have become certain, you can readjust your overall plan, and in that sense, a strategy is composed of smaller sub-plans, which we call tactics. Yeah, here is now finally, the really first interesting thing we do today. Here's an observation. If we knew the complete game tree of a game and the payoffs of the terminal nodes or the leaves of the game tree, we can solve the game. What does it mean to solve a game? That is, in the case where we know the complete game tree and the payoffs of all the leaf nodes of the tree, we can indeed determine the outcome of the game if we assume that both players do not make mistakes. If both players play optimally, both players are infallible opponents and never make a mistake, under these circumstances we can actually say what the game will end in, what will be the outcome of the game. And this is best understood by looking at an example, right? And here is the example we are going to study. It's again tic-tac-toe. And we will again consider a game tree for tic-tac-toe, which does not start at the initial position of the game of tic-tac-toe, because then again the tree will be fairly large. So we start further down. Actually, we start even further down than we did so far. This is a state during the game of tic-tac-toe where there's, I don't know, it's actually the same depth now that I think of it. 4 fields left, 4-player not to move. Right. Let's see how we could solve this game. Like, given that this initial, it's not really initial state, but say this were the initial state of the game, what will be the outcome of the game? A draw. How do you know?
We assume that nobody's making any mistakes.
Yeah. Well, why would that then end in a draw? Now, this is, of course, I know that it is common sense, or common knowledge that tic-tac-toe will end in a draw. We know that. But let's see how we can actually determine that through computation. So this is the situation we are starting with. Right? We have this state which we declare to be the root node of our game tree. And we know that in this state, player naught is to move. And obviously, so then at the next point in time, it is player cross to move, and then player naught, and then player cross. Right. This is how we start. And we do know, since we do know the game tree of this game, we may also compute the payoffs for the leaves. Right. Once again, typically we don't really know the game tree, because they can be very, very large, and there are games out there where people or humankind has not yet computed the complete game tree. But for tic-tac-toe, we are fairly safe. We know this is the game tree in this situation. Now, what do we do? The algorithm proceeds as follows. We can think of coloring the leaf nodes according to the outcome for player O. Player O is the one to move here. And let's use the following convention. I mark every leaf node that indicates a situation where player 1 will win using a blue square. And every leaf node where player naught will win is marked by an orange square. And of course, the situations that end in a draw are marked by a black square. Say. Can you visually distinguish black from blue squares? Might be, it's okay? Okay. So there are blue squares here, and then there are some black. And if you don't really, because of the resolution of the beamer, can distinguish them, then have a look at the slides I will upload to the website. Yeah, so this is the situation we are studying with. We do know the game tree, we do know the leaves. For the leaves, we do know the payoffs, and we encode them using this coloring scheme. All right, now, what do we do next? The algorithm proceeds as follows. We basically iterate over the levels of the tree, starting at the bottom. Pardon? So we start at the bottom, look at the information that is available there, and sort of propagate it to the higher levels of the tree. Say we consider one level in the tree and say this node. And if that node is not yet colored, so if we have a look at the situation where we start with, so we want to sort of color this node, it is not yet colored, and we are considering this level of the game tree. And it represents a state where player P is to move, in this case player cross. Then we set the node in question to the color of all the children's that would indicate the highest payoff for P. And in this case, this is fairly simple because this node just has one child node, and that child node would actually indicate a win of player 1. So the highest payoff of player 1 is actually, say, player 1 will win. So we just propagate this blue color to that node. Right? This is a node where player 1 is to move, and the outcome of the only child of that node is a draw, so the highest payoff for player 1 in that situation is indeed a draw. And on this level of the game tree, there are no further other interesting situations to study, so let's go one level up. This is a node where player 2 or player not is to move. And so we are now interested in what kind of color we should assign to that node. Right? This node now has 2 children. One of them is marked in blue and the other in orange. And player orange, player 2 or player not, as you like, is to move. So we should assign that color to this node of all the children that maximizes the payoff for player not. And this is of course orange. Because again, like in this situation, in this child node of that game state, player not would win. So here we go. That is, we have propagated this information up the next level of the tree. And then we are dealing with a level where it is again player X or player cross to move. So what kind of color would we assign to this node, say? Blue, obviously. Right? There are indeed now 2 child nodes where player not would win, so the opponent would win. But in this state, the highest possible payoff for player blue or player cross is to win. So yes, we assign that to this node. What about this node here? So this is a node where player cross is to move. It has 3 children. 2 of them are colored in orange and 1 is colored in black. That indicates in 2 situations resulting from my move, 2 possible situations. Yeah, right. This is the highest payoff for player cross here. It's 3 possible moves, 2 will lead to a loss and 1 will lead to a draw. So the best thing player cross can do is to move towards a situation that will maximize his or her payoff, which in this case is a draw. Oh yeah, it works beautifully. So, and now we can solve the game. Because now we have reached the top level of the game tree, in our example here. We can ask the question, if player O, or player not, or player 2, who is to move here, plays infallibly, right? Plays optimally, what will she or he do? Move to the state that will lead to a draw. Why? Because there are 4 possible moves here. 3 of them would lead to a win of player 1. We have established that so far, if both players play optimally. And the 4th one will lead to a draw. So if player 2 is really smart, he or she will definitely move to that state, and there you have it. This game of tic-tac-toe starting in that tree will end in a draw if both players play optimally. It is solved. We know that. If we know the game tree, and the payoffs for all the leaves of the game tree, we can determine the outcome of the game. And again, that sounds great, but typically we don't know the game tree. Right? But once we have sort of run this process of backward induction, this is how it's called, we can color the root node of the game tree, and that color determines the outcome of the game. Now, yeah, you already told me that tic-tac-toe will necessarily end in a draw. Right? And it is indeed true. You can actually compute it at home because the game tree of tic-tac-toe is not that big. You can do that, and you will find if you use this algorithm, it will always predict the game will end in a draw. And this is a central idea or key plot point of this classic movie. It's from 1983. It's the first Hollywood movie I am aware of where computer games played a central role. there's this crazy intelligent computer that goes nuts, and they have to try to convince the computer not to start an atomic war, and they do so by having the computer play lots of games of tic-tac-toe until the machine realizes there is no winner. And once the machine has realized that, it blows off or cancels World War III. So this idea that tic-tac-toe necessarily ends in a draw is indeed a central motive of that movie. I already told you last time that checkers has been solved, and now we understand the notion of a game has been solved, like from the point of view of game AI. The complete game tree for checkers has been computed, and once it was available after fairly long time of computation, you could run this backward induction argument. And it turns out checkers will end in a draw. And if you're interested in details, here is this paper published in Science in 2007, which is indeed entitled Checkers is Solved. It's done by the Alberta Games Group, the University of Alberta in Edmonton. There is a department, a computer science department. There's a chair on AI, which is sort of famous for having studied more or less game AI exclusively for the last 20 years, 18 years of computation time. So the Alberta Games Group has established that checkers is solved. And it will end in a draw. What about other games? We can solve Connect 4. Can compute the game tree for Connect 4. Is a bit larger than for the case of tic-tac-toe, not nearly as large as in the case of checkers. And we can do that. We can compute the game tree for Connect 4, and turns out, under the assumption of optimal play, the first player to make a move will always win. If both players play optimally, the second player cannot win. So that is for Connect 4. This is great. This is great. We now know that if we knew the game tree, we can solve a game. But that is, of course, not the situation we are facing while actually playing a game. Right? This was sort of a bottom-up process, starting with a lot of information available to us, game tree plus payoffs at the leaf node, propagate that information back to the root node of the tree. But of course, gameplay happens in a top-down manner. The states or the nodes of the game tree sort of are uncovered one at a time. We start, in the case of tic-tac-toe, with an empty board. Player 1 makes the first move, player 2 makes the second move. So if we eventually uncover the game tree, how can we realize optimal play from this point of view? Right? Assuming that the game tree is not yet fully available to us, but sort of just is being developed while playing, and we probably have to look ahead and stuff like that. But how can we use the data structures we have familiarized ourselves with in order to realize optimal play? And this question leads us to one of the famous accomplishments of early AI research, and basically, as we will see, to sort of the standard solution for how to play two-player turn-based zero-sum games. But before we'll do that, here is a couple of things. Here are a couple of things I have to fix in advance, so that from now on you will follow me. In what is to follow, I will always refer to the player who is to move in whatever game state we are starting our consideration. The player who is to move in the game state we are starting from is called max. And the opponent will always be called min. And I'll call arbitrary game states n, right? Just some indicator, some name of some node in a game tree will be n. And in particular, I will not be very careful with my terminology. I might indeed use, or will possibly, the terms game state and node, or game tree node, interchangeably. To me, they are the same thing. The game state and the node in the game tree are the same thing, so I will not be very careful in trying to distinguish them, so don't be surprised. And I will also, most likely, I don't even know, I should have looked at my slides, but most likely I will refer to game trees as game trees or as search trees. Right? Again, to me, they are the same thing, and we will see why. And here is sort of the reason for using this terminology. Now we already said, well, we have game trees. They are leaf nodes. They are labeled with utilities or payoffs. And our goal in a game would be to reach a terminal game state, a leaf node of the game tree of high payoff for us. So if we are the players who make the first move, we want to maximize our payoff. Max. And obviously our opponent is trying to sort of minimize our payoff. Recall that we are talking about zero-sum games here, so the opponent is called min. And we are concerned with finding strategies. That is basically, we have to search the game tree for a path that is a sequence of moves and thus sequence of nodes leading from the initial state of the game to a goal state of high payoff. And so because this idea of search plays a prominent role here, game tree, search tree, whatever, might be the same thing. Don't be surprised. I have mentioned it a couple of times already, that when reasoning about games the way we are currently doing, we do assume optimal play. What is optimal play? We can try to formalize that. If both players are intelligent and know what it means to win or to lose, then we can think conceptually. This is of course not what's really going on in our brains while we are playing a game, but conceptually we can think of a game like this in a state n where Max is about to move. Max will try to move such that his or her move will lead to a subsequent game state from which he or her may reach a winning state. Will try to move in a direction, and when I say move towards a goal state, then I'm referring to the game tree. Max will try to move down the game tree, one level down, using a branch that will eventually lead to a win, or has the potential of leading to a win. And of course, once Max has moved, Min, who is also assumed to be an intelligent player, will try to counter that move. Will try to move such that Min, he or she, will have a chance of winning the game, and indeed actually will try to move such that Max will lose the game. So they have conflicting interests. Both want to win, but only one of them can actually win, so they will try to counter their moves. And that is to say, we can think of coming up with a strategy. And again, a strategy is a sequence of moves that takes us from an initial state to a goal state, usually a winning state. We can think of the problem of planning a strategy in terms as thinking about what to do in the current state of the game if we are to move. Right? What do we have to do? And then we decide for a move, or we can fantasize about, well, if I were to move here, then my opponent can do this and that and that and that, and among these possible moves for the opponent, this one would actually be the best for the opponent. Now, what would I do if we are in this game state? Then I could move here and there and there. And among these opportunities or ways of moving for me in this game state, this one would be the best for me. And so this is this idea of looking ahead. Well, if I make a move, my opponent could do this and that. And if the opponent is smart, the most likely choice or the optimal choice would be to do this. And in that case, I could then, among all the possibilities that are open to me in this situation, do this, and so on and so forth. And of course, we can think of this process of looking ahead as mentally expanding a game tree. When we are in some state, Max is the player to move in this state. Max will think about, well, I have a couple of possible moves, and for each move, I sort of can think about what next point in time the opponent will do. And once the opponent has made a move, then I can, again, make another move. And ideally, I would choose some move that will lead me to a winning situation. And this way of sort of thinking ahead is mentally expanding the game state, the game tree. Yeah, and then we can define the notion of an optimal strategy. Both players are intelligent, and both players do think ahead. Then what is an optimal strategy? Again, a strategy is something that takes us in a series of moves from the initial state to a goal state. An optimal strategy is, funnily enough, at least as good as any other strategy that will take us to a winning situation. This is a rather weak prerequisite for something to be optimal, right? It has to be at least as good as anything else we could do. I'd move at random, and if we're really lucky, this may take us to a winning situation very quickly. It's very unlikely, but could happen. Of course, it can also lead us to a situation where we will lose. And in that sense, a optimal strategy has to do better than this random moving. But there are very, very good strategies that pop out of random moves, so we have to be at least as good as that one. How do we find such a strategy? Yeah. We will see that it is very easy to come up with an algorithm that does that. But, writing it down is no problem at all. But it is usually possible or infeasible to use that algorithm in practice. And that again has to do with the size of the game trees that do evolve while we make this look-ahead kind of planning. So coming up with this algorithm is very easy. I will do that in a second. Using it in practice is close to impossible. And in the next couple of lectures, we will then look at ways of how to modify this simple algorithm such that it becomes applicable. And in particular, that will require us to introduce heuristics, and we'll have a look at some of those. Okay, once again, for what is to follow, we do assume that both players, Max and Min, know their payoffs for the terminal states. That is to say, Max recognizes when he or she has won, Min recognizes when he or she has won, and they both know what it means to win in terms of the numeric value of winning or losing. Right? For the sake of simplicity, we'll assign a +1 to leave nodes where Max will win and a -1 where Max will lose. 0 for draws. And here is the mental process of player Max when he or she is about to make his or her move. I should move in a direction, and again by direction I'm referring to picking an edge of the game tree that will lead to the next game state from which there are good chances that I will win the game. I should move in a direction that maximizes my payoff. If I do so, my opponent Min will try to counter my move and move in a direction that minimizes my payoff. We can agree on that. So then what should we do? And the answer an optimal player, a player that plays infallibly, will give is, hence, I should move in a direction that maximizes my minimum payoff or minimizes my maximum loss. Right? Might be, for instance, like consider a game where you play for money, poker, or whatever, and you find yourself in a situation where you know I cannot win this anymore. Right? This is a losing game for me. Okay, we can abandon all hopes and say whatever. Right? I'll gladly pay $10,000. Or we can say, well, okay, this is not to be won anymore, but at least I can try to minimize my losses. And there are possibilities of losing $10,000, $1,000, and $100. And I should definitely go for the way that will, where I just lose $100. So I have to minimize my maximum loss. Right? And of course, the other player, while playing for money, says, okay, I will win this. We have reached a state of the game where I cannot lose anymore. And apparently there are ways for me of making 10,000, 1,000, and 100 bucks. And I should probably try to move in the direction that will earn me $10,000, right? But again, then when I'm doing that, then the opponent will try to counter that. So probably should be satisfied with the 100. You see, this is the kind of reasoning that's going on here. I could boldly move into the direction where I might win $10,000, but I probably might not actually win that. If I move in the direction, and we'll see an example where I might win $10,000, I might actually end up in a situation where I just win $1 because there was a possibility for the other player to counter that move. But if I were to move in the direction where I can win $100, I will actually really win $100. So this is the reasoning of the player who has to make a move, max. And remember that I told you that in a zero-sum game, one man's loss is another man's gain. And this leads to the idea of the famous MinMax algorithm. And that is, in one sentence, a decision rule, whatever that is, for how to play an infallible opponent. How to play against adversaries that do never make mistakes. And the idea in a nutshell is to minimize my possible maximum loss, which is the same as to maximize my possible minimum gain. And we can formalize this idea using game trees and payoffs for the leaf nodes by assigning a so-called min-max value to every game state that can result from the game state n we are currently in. And once we have computed the min-max values for all possible successor states, we will move to that state with the highest min-max value. Okay, and this can be computed very simply. It's easy to compute that. It's easy to formalize this idea in terms of a recursive function. So say we are in some state n, which I call n naught here, because there are a total of 12 states, 13 states. And we do want to, it's our move, so the blue player has to move. The question is how to compute the min-max value for n naught. Well, if this was a terminal state, it would be easy to compute the min-max value because we would just, use the utility or payoff function. But this is not a terminal state in this example. So, therefore, we, in order to compute the min-max value, have to decide which player is to move here. And, we said it's max. The one we start from is always called max. So, max has to choose a move towards a successor state that sort of maximizes his or her payoffs. So this is a node where max has to move. And max is trying to maximize the min-max value of maximum for this node. Now, So therefore, let's recursively compute that. So we don't know the value of this node yet, but let's see if we know the values of these nodes. We don't. Right? But we know that on this level of the tree, it is player min to move. And player min will try to minimize the outcome for max. So player min will try to minimize or choose that successor node with the lowest min-max value. The minimal min-max value. Right? But we don't know these min-max values yet, so we have to compute them. So we go down one level of the tree and we realize, oh, this is a terminal node for which we may know the payoff. We can tell this node about the payoff, but there's more children, so we have to look up here and look up there. Once we have seen them all, we can actually compute the minimum. Once we have computed the minimum here, we can propagate that back up and then have to go down this subtree to compute the min-max value for that node. And once we have computed, we can propagate it back up, but we still have one node unexplored. So we have to go down that subtree. Once we have computed the min-max values for these three nodes, we can actually set the min-max value of that node to the maximum of all the min-max values of the subset nodes. All right? Here is how that happens. So we go down this branch of the tree and we find A6. So this is not tic-tac-toe, this is playing for money, say. And the numbers assigned to these nodes are sums, amounts of money Max could win when reaching that node. So in this case, it would be A6. This is great. We propagate it back up here, but we're not enough information yet. So next node would give us a 15, which is even better. And then we have a 3, which is sort of a downer, because now player min, in this situation, where the three successor nodes would yield payoffs of 6, 15, and 3, would definitely go for 3. Player min would minimize his or her losses. And when faced with the decision of paying $15 or $3, everybody would go for 3. All right? So, we know in this situation, player min will go for this terminal node. Yeah, we can propagate that back up, but we have to go further down the second subtree in this case. And for this leaf node, we find a payoff of 3. Then here is a payoff of 2. And here is a payoff of 10. What will player min do? Go for the 2. Right? Definitely. There is no question about this. Player 2 is an infallible opponent. Will never make mistakes. Will always do what is best for him or her. And final subtree, we again, have gone all the way down, find a 6 here, go back up one level, go back down one level, find a 17 and find a 7. What will player min do? Go for the 6. All right, now, then what will player max do? Go for the 6. Let's see. That is comforting. This is how it works. Do you understand that, right? This is a very trivial recursive computation. Can we already identify a serious problem with that?
We have to traverse it.
Exactly. This is a depth-first search algorithm, right? And we have to, in order for this node to compute the min-max value, we have to go to the bottom of the tree for all the subtrees following from this node. And the reason why I'm showing you this example is because, this is a trivial tree. Everybody can, look at this tree and see what's going on. But again, for tic-tac-toe, if we were to start at the root node, the tree would be fairly large already. And for chess, it has not been computed yet. Here are some more examples. I am just showing this to you to indicate that whereas in this initial example we had a tree with a constant branching factor of 3, number of children of any non-terminal node is 3. Of course, this simple algorithm does not really care about the number of successor nodes, the number of children of one node within the tree. Right? So here we have an example where the root node has 3 successors, then there is one of these successors has 4 children, the other one has 3, and the other one has 2. So it does not matter. We can use this algorithm. And in this case, we'd find that the maximized minimum payoff is the minimized maximum payoffs for player 2 are 11, 5, and 14. So the maximum out of these minimal payoffs would be 14. So player 1 would go for the last branch. Yeah, it's just the same example. This time, five successor nodes. It does not matter. It doesn't matter. And obviously, the depth doesn't matter as well. Right? We can run this algorithm for trees of, arbitrary depth. It may run for a while, though. It may run for a while. These are all trivial examples, right? This is 5 levels, no problem here. We can do that. It would be very tedious, however, to do this by hand already. But actually, the Python implementation I wrote to do this, it's a fraction of a second. No problem there. In all of this, we did assume that the opponent plays optimally, right? That the opponent never makes a mistake. Now, what if our opponent was not that smart? How would that affect this way of deciding for where to move? What happens if our opponent does not play optimally?
Even better for us.
Even better! Do we know why? So it's actually even better for Max. you nailed it. Why would that be?
Because if it is optimal, you choose minimum
Yeah.
value.
Yeah.
So if it's making a mistake,
Yeah.
it is more than minimum.
Exactly. Here is the formalization of this answer. He nailed it. Right? He said the optimal way or decision for our opponent is to try to minimize our payoff. Right? And then therefore, if so, this is what we have to do. We have to maximize the possible payoffs we can expect. Right? That is, we are in some state, and for the successes we compute these min-max values, and then we choose that state where this is maximum. And of course, we can expand this set, and that is to say that we have to look for the maximum of this set. But this set is composed of lots of values that have been found to be very small. Our opponent has computed this set here, and this is a set of lots of minima. And now if our opponent was not so smart and would choose another way of picking the values in this, let's say a random function, right? Could be some other informed choice, but for the sake of the argument, the opponent picks a random node. Then the maximum of this set is exactly as he said. Then this is larger than in the case where the opponent plays optimally. Right? If we assume that the minimum of a set is less or equal than some random number picked from that set. We might be lucky and actually pick the minimum. Right? This is why we have these less or equal here. But usually, if we randomly pick a number from a set, it might not be the minimum number in that set. So in that case, yeah, if the opponent does not minimize our possible payoff, but does something else, all the better for us. Now, have a look at that tree. It is, again, a fairly shallow tree. We start in a situation where player max is to move. This is the setting we look at. It will end after our opponent has moved. So right now we max make a move, then min has to move, and then we can make a move, and then the game has terminated. So these are the payoffs for this silly game, for the leaves of this silly game. And the interesting observation is that there are two nodes, N1 and N3, where our payoff is 5. So we have two successor nodes with an equivalent min-max value. And as we can basically randomly pick one of them, right? But if we were to move down this branch of the tree, then the maximum payoff we can expect is 18. Whereas if we move down here, it is 16. So where should we go?
And the opponent chooses randomly?
I don't know, like let's say it plays optimally.
If it's optimal, doesn't matter.
It doesn't matter, exactly. Exactly, it does not. Because if we move here, the opponent who plays optimally will go there. Payoff 5 and not 18. If we go here, the opponent who plays optimally will go there. Payoff 5, not 16. It doesn't matter. It doesn't matter. Right? And this is it's good to know. Right? This shows sort of the constraints this assumption of playing an optimal infallible opponent introduces. But then again, we do know that human players hardly ever are infallible. Right? So if we play against a chess computer, we can rest assured it doesn't matter. It doesn't matter. If we play against a human opponent, it might actually be worthwhile going down here. Right? Because, if the guy makes a mistake, then even better for us. But if we play against some entity, person or computer, who is using the min-max algorithm to decide for its moves, it does not matter. Here is how you could, if you would want to, maybe you have to next time, do this in Python. And again, I am using this idea of dictionaries to do that. What I'm doing in this example, I'm building a tree of two levels down and branching factor of 5. I should have called it B, not N, I don't know why. We start at some node, just register the node numbers, not really important here. Build a tree. Once we have built the tree, I'll show you how to do that in a second. We can compute the min-max value of the root node equals 0 of this tree. Here is the function I'm using to build the tree. I think we have seen that last time already when we were computing game trees. This time we are just interested in a utility tree, or this is a tree where there are utility values assigned to every leaf node, so I don't actually have to compute games. This is really abstract here. This is what we do. We enter this function with a node and the level and the number of branches, which now is set to 3, whatever. This is the default value. We initialize a list of successor nodes. If we have reached level 0, which 0 here to indicate the lowest level of the tree, whatever. We basically, for the node with which we have entered this function, we compute a random utility value. This is just, I did all the trees we have seen with random values on the lowest level of the tree. Right? So we generate one number between 1 and 20 and use that as the utility of that leaf node, and we register that in a dictionary. If the node we are considering right now is not a leaf node, that is not on level 0 of this tree, we look at how many branches we have to create, and this, like, the default is 3, but we can use some argument here n whatever to create arbitrary number of branches. We create a new node, that basically look up a new identifier of a node, register the fact that we now have a new node in a corresponding dictionary, and add that node to the list of successors of the current node. Once we have created all the successor nodes for the current node, we register the list of successors in the dictionary that keeps track of successor nodes of nodes. And then we have to recursively continue building the tree, and we do this for every successor node and decrease the value of level. And of course, once this value reaches 0, we are in the situation. So this is how we can very, very simply build such an utility tree that does not really compute a game, but basically assigns numbers to the leaf nodes. And here is how, given such a utility, some tree structure with numbers assigned to the leaves, and this is a Python implementation of this MinMax algorithm we saw in an abstract version earlier on. So this is how we would compute the min-max value in a situation where player maxes to move. So we compute the max utility of a node. If that node we are currently considering is indeed leaf node, that is, it is in this dictionary with utilities. The non-leaf nodes are not in there yet, but if it is in there, then it must be a leaf node. So we basically return that value, that utility value assigned to the leaf nodes. If it is not a leaf node, we will set the min-max value to -infinity. We can do this very easily in Python. There is actually indeed for NumPy a way of using infinity. And then this is nothing but the implementation of this max of all the min-max values of the player min. So basically we compute maximum of the current min-max value in infinity and the minimum of the min-max value of the subtree, which is computed using this function, which does basically the same as this function. The only difference is that we have an infinity here and not -infinity. But this is exactly, if you look at it, this is exactly the situation we saw in this equation. This equation, right? And if you do some further reading, and you read the literature, and you find the notion of a MinMax algorithm, then you can rest assured that is exactly the same as this here. The only difference is that it saves lines of codes, because if you look at it, here we have some minus and some max, and here we have some something positive and some min. So if we were to multiply this by -1, we would actually have the same situation as in this function. So if we had another argument which indicates the player, which we have already seen can be indicated by 1 or -1, we would, multiply these values by this additional argument. We would not have as many lines of codes, but probably would not be as readable. It's the trade-off. I don't know. There is no big difference there. So max, if you look it up, or if you do some reading, is exactly this in fewer lines of codes, just multiplying a number plus or -1 that indicates the player. That's all there is to it. I have already told you that this min-max algorithm is expensive because it is a depth-first search algorithm. This to compute the min-max value of the node we are interested in right now, the min-max value for the game state, where we have to decide for a move. We have to know what of our possible successor states has the best min-max value for us. And in order to determine that, we have to go down all the way to the leaves. And if the tree is large, that can take a very long time. Indeed, the number of states we have to examine is exponential in the number of moves. That is to say, if we have an average, I'm talking about averages here, average branching factor of b, then in the very, very worst case, we would have to compute b to the power of m, where again m indicates the deepest level. M can be very, very, very deep. I don't know. Chess ends after 50 moves, so in chess it's not larger than 50, but if we have, I don't know, we said average branching factor for chess is 35. 35 raised to the power of 50 is really, really large. So, yeah, that is something you have to keep in mind. This,
so
yeah.
We are more interested in deep trees than in shallow trees, right?
Oh, so his question was if we, in practice I assume, are more interested in deep trees than in shallow trees. So the shallow trees I have shown you here are just examples which I am using to illustrate the behavior of these algorithms, and they have been chosen such that I can actually comfortably plot them on these slides. There are very few games with shallow trees like that, and in any practical situation, that is in any situation where you use tree search algorithms to come up with strategies, the game trees will be really deep, and even for the case of tic-tac-toe, could be as deep as 9 levels because there's 9 fields to make moves. But of course, in chess that can be 50 because it ends after 50 moves. But in practice, these trees are anything but as simple as the ones we have seen here. Yeah, that is a problem. That's a problem. It is indeed actually truly usually impossible or infeasible to compute the min-max value for every state throughout the game. It's like, can't be. I mean, it can be done, but it will take very, very long time. Now, there are a couple of possible solutions. One solution, for instance, is think about something we have talked about last time. So last time, he's not here right now, but one of you was wondering why we actually were to represent all possible games in form of a tree, right? So every possible tic-tac-toe game, why to consider a game tree to represent them? Because obviously there were several nodes in that tree that occur repeatedly. Extremely valid concern, right? There are lots of game states that can result from different sequences of moves, but they are the same anyway. Right? I can place a cross in the middle, a circle here, cross there, circle there. I can play cross here, circle there, cross here, circle. It's the exact same game state, but different ways of how to reach it. Different branches might lead to the same game state. Then, of course, if we have to explore a whole subtree and then propagate everything back up and then explore the next subtree and encounter a state we have seen already, what could we do? Well, yeah, or use the information we have computed earlier, right? Okay. So once again, you start in some root node, you go down some subtree, and you propagate everything back up. And then you go down the next subtree, and while going down this subtree, you encounter a situation you have seen before, because different sequences of moves may lead to the exact same situation. And then you should stop computing what can happen from there, and just sort of look up what happened back there. Right? So that is to say, you should, in practice, make use of these lookup tables. And also, if you remember, we already talked about the idea of creating hash values for game states. Right? So a way of computing, say, numbers that uniquely identify this game state. Once you have that, you can have a table with these numbers in the first column and everything to know in the columns, like seconds or whatever. And then if, while running min-max on some other branch, you encounter a state with the same hash value as one of the states already in your table, you just look it up in your table, take the numbers from there, and stop expanding the tree. Right? So that will save you a lot of time. And this is indeed done in practice, in particular for opening situations in chess and for endgames in chess. So once the game has reached a situation where there are not so many pieces left on the board, whatever, just as in the example with our tic-tac-toe state, where we start from a situation where there's not so many empty fields left. for these situations, we can compute the complete game tree. And whatever we find there, we can put into a table so that during a real game, once we encounter such a state, we just look up in the table what is to do there. All right? Another idea is, and we'll look into that not so closely, but next week, to limit the depth of our search. Right? Not to go down all the way to the leaves, but stop at some level higher up. So say like we fix the number of look aheads to some number, say 10. We just look ahead 10 moves, but if there is like 50 moves, then of course we will not, reach the leaf level of the tree. What is the problem with that? If we just look ahead a fixed number of moves, obviously the computational effort is much less, as if we had to explore the whole tree. But we may stop our search at a node where we don't have a utility value yet. Right? And we will talk about ways of how to estimate utilities for nodes that are not leaf nodes. If we have good ideas as to how that can be done, we can use that to limit our searches to certain depth, which saves a lot of computation time. And then there is this idea of pruning a tree, and you already mentioned it. And this is basically if we, during our search, that is during the expansion of this game tree and computing the min-max values going down, propagating back up, going down, propagating back up, whatever, we encounter a branch where, and we'll study that next time, we sort of can be sure that it does not really make sense to go deeper here, because already from looking at just a few computations, we can decide that this branch will not be good for us. We don't have to explore that. That is called pruning, and we will study that next time. And this leads to the summary for today. Given what we have talked about today, we now know about zero-sum games and the idea of utility or payoff. In particular, in a zero-sum game, if we have reached a terminal state of the game, the payoff for the one player will be exactly the loss of the other, or the others, and vice versa. So, gains and losses sum to zero. You win, the other guy loses. You win $100, the other guy have to pay as much as to sum up to $100, whatever. We have seen the notion of goal states and the idea of optimal strategies. And basically we said that a goal state is a terminal state, is a leaf node in a game tree, and a strategy is a way of reaching that leaf node from an initial state, say the root node of the game tree, like a way of propagating down the tree. And a strategy is optimal if it is as least as good as any other possible way of, how to reach that state. We could, not really think about it, just, randomly propagate down the tree, and if we're lucky, we end up in that state we want to end up in. But we may as well not. We may have different functions that compute how to, proceed down the tree. We'll look in some of them. And they may lead us there, or they may not. An optimal strategy should, guarantee that we will reach that state. If any other strategy does it, then the optimal strategy should do it as well. Sort of weak notion of optimality, but there you go. And then we have looked at two things we can do with these game trees, two kinds of computations. I first told you about the way of solving games once the game tree is available and we have payoffs and utilities for all the leaves. We can solve the game, that is, we can compute in advance how a game will end if both players play optimally. And then we looked at the famous min-max algorithm, which is the standard way of indeed computing strategies for turn-based two-player games, zero-sum games. It is optimal. It will always sort of, find the strategy that is best for us if both players play optimally. But there are issues there with respect to computation time and memory use and so on and so forth. So that is all for today. Next time we will look deeper into that, in particular into ways of sort of how to improve or speed up the computation of min-max values. Are there any questions?
The MinMax algorithm is not good to earn more.
Yeah, so his
Because
question
you
is...
make a risk.
Yeah, no. His question is like the min-max algorithm does not guarantee that we will make it big, right?
Yeah.
Like win a lot. No, it does not. It does not. Yeah. I've still not decided whether or not during this lecture we should actually look into mathematical game theory. This is a field of mathematics or the economical sciences where people actually study under which conditions different participants in, say, game situations, and economy can be thought of as a game, under which conditions who will win or lose what. And there are a lot of things known from this area, right? Indeed, we do know that this is not very human, and if it was, you would not have asked. We know that, like, under these assumptions of optimality, this is the best you can do, right? Of course, people are greedy, and people are not necessarily rational. So people may say, well, yeah, but if I go here, I can earn $10,000. But then your opponent goes for the solution that earns you 5, and in the other situation, you could have earned 100. Like, I don't know, in the other situation, the maximum you could have earned was like $1,000, and the minimum was 100. And you go for the situation where you say, yeah, here I can earn 10,000 or 5. And so I go for the 10,000 direction, and if your opponent is smart, he will then move in the direction where you earn 5, and you have sort of lost $995. So no, this does not guarantee that your payoff is maximal, but it guarantees that your minimum payoff is maximal, which is the take-home message today. If you are smart, you are satisfied with the max of the min. If you're greedy, you are satisfied with the max of the max, which is hard to attain if your opponent is smart. Any other questions? Great. Again, Thursday is a holiday, right? So we'll have that a lot throughout this semester. So see each other again next Monday. Thank you.